for this session today. We're going to go ahead and record this session because not everybody can make it at this time, and we've been requested to record these sessions so people can come back later and watch them, as painful as that might be to watch me later. I will go ahead and share my screen here, and we can get started. All right, now, I know that several of you on the call today are seasoned data managers who have been dealing with the data management stuff for quite a long time. And to you, I say, hopefully this is a useful refresher. Hopefully you're not just twiddling your thumbs and wishing you had this hour back. But to the rest of you who are joining, I hope what we say today is going to be useful as you think about the data products that you're producing as you're doing your research. And we are doing this particular session at the request of one of the CZNet principal investigators who said it would be really great to have a session for graduate students and others who may be relatively new to the data management game and cover some topics that might be good for pretty much anybody to really be thinking about in terms of data management. So the title of today's talk is Simple and Effective Methods for Managing and Sharing Scientific Data. And I would like to plant in your brain right at the beginning here the idea that data are first-class products of research. So just like the academic papers that we produce, all of the other products we're producing as part of our research, data are first-class products of research. And there's a lot of groups that are sort of hovering around this idea. And one of them is this Force 11 data citation synthesis group. And they've come up with a set of principles related to data citation that I think are useful just to look at briefly. So their number one principle, data should be considered legitimate, citable products of research. Data citation should facilitate giving scholarly credit and normative and legal attribution to all contributors to the data. And then in scholarly literature, whenever and wherever a claim relies on data, the corresponding data should be cited. That's certainly a different way of thinking than at the beginning of my career personally. And I hope this is not necessarily new. I hope you're starting to see this all over the place, because when we think about data sharing and data sharing requirements, it's really quite common now that the grants that we're working on are requiring data sharing and availability. If you submit a proposal to the National Science Foundation, you get to submit a data management plan that explains what sort of data you're going to collect and how you're going to manage that data over time. And it's also true that many scholarly journals, including all American Geophysical Union journals, many other journals that I've seen recently, have data publication and citation policies that basically stipulate if you want to publish in our journal, you get to deposit your data in a reputable repository, unless there's a very, very good reason why you can't do so. And there are some exceptions to these policies. But they're basically telling you if you want to publish, you get to deposit your data in a repository. And data is pretty broadly defined. It could be the numbers that you use to generate or display in the figures, graphs, plots, videos, animations, or tables in your paper. But it could also be things like protocols and methods used to generate the data in the paper, the code and computer software used to generate the results or analyses reported in the paper, and then also derived data products reported or described in the paper. So if you look at like NSF's requirements for data management plans, they will describe data much more broadly than maybe you think about data on a day-to-day basis. So there's a lot of publications out there talking about data management and how some of our past practices with data management and sharing data are maybe not good enough. The past practice of putting a statement in a paper that says, if you want my data, please contact me, is not really good enough for publishers anymore. And we see statements like, when you publish a research paper, you are also simultaneously publishing the data that supports your work, and the readers of your article have rights to see both the words and the numbers, because how can they actually prove or reproduce the work that you did without actually being able to access the data? So that brings us to the question of reproducibility. I've got a little figure here that depicts the scientific process, and you could Google scientific process and you would get any number of diagrams of this process. There's nothing really special about this one, but when we think about data in this process, communicating and sharing data really is an essential component of that process. And if our science is not reproducible, it's hard to say that we've actually completed the loop and accomplished what we sort of buy into with this scientific process. And so in a lot of ways, the value of data sharing has not been fully realized yet, although I think a lot of people are now realizing, yes, data sharing is a good idea. Yes, my funder is requiring me to do this. Yes, I need to deposit this when I publish my paper. And yes, it's actually a really great thing when somebody can reproduce the work that's in my paper and then modify it and build upon it. So how are we doing as a scientific community? The plot in this graph is from a paper that was written by Jim Staggy, who was here at the Utah Water Research Lab for a while as a postdoc. And he and a bunch of students at the Water Lab pulled 360 papers out of a bunch of water science, water resources journals. And then they read the papers and tried to reproduce the results that were reported in the papers using the statements in the paper about the availability of the data and artifacts that they needed to reproduce them. And there's been a bunch of studies like this. This is just one out of many that I've seen. The real result that is sort of staggering here is that they were only able to fully replicate the results reported in 4 out of the 360 papers that were published. So you can see the various reasons why the data were not available. Some of the data were available. Some of them had statements that you had to contact the author to get the data. Some had data, but there were no directions and code. Some had code, but no directions. Like all of these sorts of things contribute to the ability to actually use the products that we're producing. And I think it's good to keep in mind this idea of information entropy. So on the left-hand side of this plot, we've got information, content of data, and metadata, and that's probably highest at the time we actually published the paper that describes what we did, and it may have some of our data associated with the paper, but over time, we start to forget the specific details. We start to forget about the problems that we experienced with the data, specific dates, things like all of those little minor details start going away. And then over more time, we start losing some general details. And maybe we have an accident or a failure of some hardware, some computer hardware, and it destroys data or documentation. People retire and they take a lot of that information with them when they go. And people eventually pass away and we lose a bunch of information that was sort of that institutional knowledge ingrained in those people. And so this is an example of how information degrades over time. And we need to keep this in mind because we don't necessarily want this to happen, even though in a lot of cases it does happen. So continuing along this line of information entropy, so here's some quotes from a few papers that I've pulled out that I think are actually good. So don't underestimate your ability to forget details about a study. It will happen. Sometimes we don't look at our data. We don't do all of our data analysis until years after we've actually collected the data. So if we're not sort of keeping good records, we can forget some of those details. Here's another one that's really important to keep in mind. If the information on an observation is lost, it's lost forever because it's almost impossible to measure that observation again in the original context. So, you know, if you went out and collected a bunch of data related to a storm event or something like that, you can't get that storm event back. You can wait for the next one to come along, but you can't really reproduce those events that happen. And so if you don't think about this up front and make plans to preserve that data, you could be out of luck. Also, if the rewards of the data deluge are to be reaped, then researchers who produce these data must share them and do so in a way that the data are interpretable and reusable by others. So we've all heard of the data deluge. We've all heard about how data are getting larger and more complex. If we really want to be rewarded by all of that data, we need to be a bit organized in the way we're approaching this. So here's another idea that I'd like to plant in your mind. So instead of that first plot that I showed you about information entropy, What if instead we curate our data in a trusted data repository? We publish a paper that uses the data, and we describe in detail the methods that we use to collect and analyze the data. And then potentially somebody else comes along and annotates that same data and uses it for another publication. The value of those data may actually increase over time, and the information content of those data and metadata may increase over time as they're used by additional people. Okay, so what do we want to do? As investigators, as students, as researchers, we want to be able to easily create a digital instance of a data set or model. Maybe we want to share it with our colleagues privately at first because we're not ready for prime time. We're not ready for it to be out there. We still are working on our paper. Maybe we're iterating on the data. It's not quite right yet. So we want to add some value through that collaboration. There's some annotation with metadata and iteration. Of course, we want to make sure that our metadata is complete. And then eventually we want to put our data or whatever products we're producing in a repository and formally publish. And that's publish with a capital P, meaning we get a digital object identifier that we can actually cite in the paper that we also hope to publish. So how do we actually go about doing this? That's going to be the subject of multiple of our upcoming workshops that we're going to do over the next several weeks, months, in fact, because we've got the holidays sort of stuck right in the middle there. So I'm not going to answer all of these questions today, but over the next several weeks, if you join us, you'll hear more about each one of these sorts of things in this workflow. But I want to focus some time today on what it means for data to be fair, first of all, and then I'm going to talk about some simple practices that you can use to make sure that your data can easily be shared in the repositories that we'll talk about later on, and will be most useful for people to discover and potentially reproduce the work that you've done. So hopefully all of you have heard about FAIR. FAIR stands for findable, accessible, interoperable, and reusable. There are actually 14 guiding principles that make data fair. And if you want to read about those, these slides are going to get posted. These links in each of the slides will take you to the papers where you can actually read about these concepts. So findable means that the data have enough metadata and a unique persistent identifier. They're located somewhere on the web that you can actually discover them and find them. Accessible means that you can go there and you can actually access the data in a way that's understandable to you as a human, but also in a way that a machine could actually go and get those data. Interoperable means that there are metadata associated with those data that conform to some standards and that people can understand those metadata in a way that they could actually be integrated with other data sets. And reusable, meaning, again, the metadata are clear. There's a clear usage license and information about provenance, meaning how were the data created, what were the methods used, and enough information that somebody could actually decide whether they're useful for a particular purpose or not. So on the CZNet website, I've listed all of these references. There's some references up there, guidelines for structuring and formatting data, guidelines for citing data, guidelines for making data more reusable, and then also for selecting a data repository. They'll also, this PowerPoint slide again will be posted for you to take a look at. These are good reads. All of them are good reads. So if you've got some spare time, it's worth looking through these. Not all of them are going to be totally relevant for every single person, but most of them have really good information in them. I'm going to spend most of my time talking about this very first one today. It's going all the way back to 2009. It's a paper that came out of an ESA bulletin. It's really, it's pretty brief. It's a pretty fast read. So if you have some time, it's worth actually reading this paper. And it's an oldie, but a goodie. And I say an oldie because it was written in 2009. And I say it's a goodie because the good practices tend to stand the test of time, right? So we're now 2022 almost. And I think the things that are in this paper are still very, very relevant today. So we're going to talk about data management 101. I take no credit for these ideas because, again, I'm using information that came out of this paper. And simple guidelines to improve data management. There's some great benefits here, though. So improve data organization, facilitating analysis of your own data and your data by others, improve reproducibility, improve capacity for data reuse, and also these are ways that can facilitate compliance with your funding source mandates and publishers when you go to publish your paper. So number one, don't mess with the raw data. Always store the data uncorrected with all of its bumps and warts as described by this paper. Because if you change the data, you correct the data to remove obvious errors that you think are errors, you could actually change something that was correct, and you could make mistakes while correcting other mistakes. So I'm not saying you don't need to correct your data, because if you look at this plot that I have here, this is a time series of specific conductance data that we collected in a stream in Utah. There's some obvious issues with the data here that we had to go back and clean up. There's a whole section of data where my sensor was actually frozen in the ice, and that's a bit of a problem. So we've removed all of that, but we've created a completely separate version of the data and saved the raw data so that anybody could actually see what we've done, and you can access the raw data. You have the quality control data as well. And anywhere you're doing these sorts of transformations, it's a good idea to script them and write your results to a new file or a new copy of the data to make sure that you could always go back and do the same thing over again. Because if you decide you didn't like how you did step number 283 in your quality control script, you can modify it, you can rerun it on the raw data, and you can get a different result that better reflects what you think the quality control data should be. Okay, number two, use descriptive file names. If you look at this example down here on the lower left, this may not be the best example of file names. So we've got junk, junk one, junk two, and oftentimes when we're doing data visualization or analysis, we create a whole bunch of intermediate files. And sometimes it's easy to just sort of let them accumulate in the folder that we're working in. And if we don't go back and clean up later, or at least use file names that describe what we're actually doing, we can, a year later, go back to this folder and go, oh my gosh, what's the right version of the data in here? Is it the stream data 2, stream data final, stream data modified, or is it stream data final, use this one, right? So I'm guessing that most of you probably have folders on your machine that look something like this. Use only plain ASCII characters and avoid spaces. And the reason for that is because when you're moving files across different file systems, different operating systems, different computers, different software programs handle file names differently. And so it's a good idea to just use ASCII characters and avoid spaces. Brief names that are indicative of content. And then because you can't include a huge amount of content in a file name, it's actually a really good practice to put a README file in the directory, especially when you've got a whole bunch of files in that directory. So this example on the right, I don't really actually know what's in any one of those files, and maybe those file names are okay, but there's a README file in that directory. And I know that if I open that README file, I'm probably going to get a description of what's actually in that directory. So that's a good practice for anybody who is producing a data set that consists of a collection of files and not just one individual file. All right, use descriptive headers in files and tables. So the example that I've given you here is a data set that I actually downloaded from the United States Geological Survey's National Water Information System. This is streamflow data, discharge data for a USGS streamflow gauge. And you can see at the top of the file, they've included a whole bunch of stuff, including a warning about the fact that you got this data from USGS, they're released on certain conditions. There's a file format description link. There's information about the query that I used to retrieve this data. There's information about the site where the data were collected, the parameter that it represents, and the actual units of the measurement. And then some data value qualifier codes are defined here as well. So there's a whole bunch of information in this header. And then if you go right down to almost the beginning of the data, the column header names are there, and they even define the actual format of the columns in the next line, and then you actually get down to the data. So a couple of things here. This is a standard convention for many software applications. So if I were to open this file in like Microsoft Excel, Microsoft Excel is going to know, okay, there's a bunch of stuff here at the top, but when I get down to the columns of data, Excel can basically interpret a delimiter that you tell it, and it will divide this data into columns, and off you go doing your data analysis. And it also encapsulates the data and descriptive metadata together so that they don't get lost, right? They don't get separated. If I hand the data file to somebody, the metadata are also there, and I actually know how to interpret this data because I have everything I need in this one file. Now, I talked about how this is a standard convention for many software applications. A lot of the data that you work with is actually going to be tabular data, right? And the convention is the first line has the definition of the columns. And in these cases, like I can look at these tables and I can sort of start to understand them. But I don't exactly know what these column headers mean necessarily. And so again, it's useful, even though I've got column headers that define all of my columns, I've got a file that goes with that defines each one of those columns, what the names of the columns are, what the units are, information about each one of them, so that when somebody gets my data file and they get this accompanying file, they can interpret exactly what the numbers or text in each one of those columns actually mean. That saves you a lot of phone calls and emails. All right, number 4, archive data in non-proprietary formats. So I always tell the students in my hydroinformatics class this. So Microsoft Excel is widely available and used now. It's probably going to be widely available and used in 10 years. I don't know, about 20 years. Microsoft Excel is probably not going anywhere. But what about other software programs that you use to create and manage data? Are the file formats that you're using with the software that you're using, can you open those file formats with a variety of software? Or can you only open them with the software that you actually use to create the data? Will your data disappear if the file format or software that you use to open that file format become obsolete? And if you want to share the data with somebody else, do they actually have to have that software to open the data file that you want to give them? And what if that software costs $5,000 for a license or even $10,000 for a license, which some scientific software can actually cost a lot of money? Are they going to be able to actually access the files that you give them? And so, of course, the question that follows up on that is obviously, what format should I use? You should store data in file formats that can be used by many different software programs. And just as an example, text files seems really simple. Comma-separated values, text files for tabular data, for example. They've been around for almost as long as computers have been around, and probably will be around as long as computers have been around, because they're simple, they're open, which mean, and by open, I mean pretty much any software program that can deal with tabular data or text data can open a CSV file. So that's a format that stood the test of time and really is platform software independent. And there's some other considerations here. So not just the file type, which is going to affect which types of software can open the data, but also think about the syntax of the data in the file. So that's how you structure data within the file. Many of you may have experiences where you've gotten data from someone, or you've created data, or you've been working with somebody and you got this Excel file, and there's a table of data over here, and then there's another smaller table of data over here, and there's a little table down here, and then there's this one's like highlighted in red and this one's yellow, and there's all of this sort of syntax in that file that you have to sort out and figure out. And if you're not the person that created all of that stuff, it may be hard to actually interpret it. So when you're organizing the data within the file, think about the syntax and how other people might actually be viewing or using that. And I separate syntax from semantics, because by semantics, I mean, when I have a column of data, what do the values that go into that column actually mean? Let's say it's a text column that defines the variable that you measured. Where do you get the names of the variables that you measure, and how do the names that you're using compare to the names that, say, another investigator in one of the other thematic cluster projects or another project you know of might be using? Are you using the same names to describe the same variables that you're measuring. Okay, so here's some best practices for tabular data, and these come from this paper that's referenced down here at the bottom. Each row in your table, if you can, each row should have a single observation. Each column should represent a single variable or attribute. Every cell should have a single value. There should be only one column for each type of information. And then don't mix data types within columns. And a lot of these practices are best practices because somebody's going to want to get the data, and then they're going to want to load the data into, say, Microsoft Excel, or they're going to want to open the data as a data frame in R or Python. And the way you've organized the data in these columns can have a really significant effect on the ability of those software programs to actually interpret what's in those columns. For example, if you're overloading a whole bunch of information into one column, it might be read as a string instead of a bunch of numbers, and you really want it to be numbers in your software program so you can do some summary statistics or something like that. So you can cause all sorts of problems for reading the data if you're not parsing it out in a granular way. Use standard formats within cells, so be consistent. Avoid special characters where you can, because things like programming languages have special characters where the plus sign, the minus sign, the asterisk, the // those mean specific things to programming languages. And if you're using them in your data, your programming language might get confused. Also use standard date formats. So the one I've suggested here, year, dash month, dash day, that's the beginning of an international standards organization date format. Use standard date formats and be consistent about the way you're encoding dates so that there's never any confusion about the way you're encoding those things. Another gotcha when using data in software programs like R or Python or other analysis programs is using null and no data values correctly. Because if you get those wrong, it can affect your data visualization and analyses. You can exclude data that maybe should be included. So for example, if you have censored data values or something like that, and you should be including them in any summary statistics that you're collecting, you need to make sure that you're handling those null and no data values correctly. Okay, number 5, consider data entry. Anytime we collect data, there's going to be some sort of data entry, whether that's you recording observations and notes in a field notebook, whether it's you transcribing those field notebooks and field sheets into some digital form like a spreadsheet, or whether it's the data logger that you program processing sensor data streams into a database. Those are all forms of data entry that have to happen. And when you're creating data entry tools, it's good to consider things like pre-designed forms or templates. This is great when you're going to the field to make sure, number one, that you fill out all of the things that you're supposed to do when you go to a data collection site. But it also makes sure that you can do things like using lists of valid values rather than free-form text entry. So if I send somebody to the field to record a set of variables, and I send 5 different people to the field to record the same set of variables, somebody might write down temperature, somebody might write down just T, somebody might write down temp, somebody might write down just TEM, and then somebody's job is going to be to compile all of these data together. And now you've got 1, 2, 3, 4 ways of describing the exact same thing that you now have to sort out after the fact. It would be better to use a list of valid values that you can choose from rather than letting everybody sort out, well, I'm just going to record T. It's also a good idea, if you can, when you're entering data, to use validation checks. And a good example of this is something like a range check. If you are measuring pH, it has to be between 0 and 14. And if it's not, there's a significant problem with your data, right? So using a validation check helps you catch those kinds of data entry errors early in the process. All right, number 6 is automate analyses. When you write code, code creates reproducible results. I can always rerun that code. And if my code is generating a plot, like the example in this slide, I can rerun that code and I can get the exact same plot every single time. Now, I could take the same data and I could put it in an Excel spreadsheet and I could generate a plot that looks exactly like this in Microsoft Excel. It's probably going to take me a couple hundred clicks in Excel. And if I handed the same data to 5 different people, I might not get the same plot. I might get subtle differences in the way they organize the data and all of that sort of stuff. So your code is a record of the steps involved in processing and analyzing data that you can go back and you can reuse every single time to get the exact same result. And this is really handy if, say, you get your paper back from the editor of the journal you submitted it to, and it says, well, I don't really like the colors that you used in figure 7. You can just go change one line of code, rerun it, and you get a new result with a new color and everything is good. Instead of opening up your Excel spreadsheet, clicking 500 times, figuring out which color looks good, and then doing all of that. Code can also be shared. So if I want to, say, share my code with my data in a way that somebody can actually rerun my code and actually generate the plots that are in my paper that was published in a journal, that's a great idea that a lot of people are doing now. And a lot of people are sort of a bit overwhelmed by the initial investment that's required to learn how to do some coding in R or Python or something like that. And I would just say to that, the initial investment to learn is going to pay off lots of dividends later. It's totally worth it to learn how to do this. Okay, number 7, consider storage media. So some of you on the call today may not even recognize some of these storage medias, right? So 1976, the 5¼ inch floppy came out. About the same time, 1985, 1986, 3½ inch floppies and CDs came out. Like, I don't even have a CD drive on my computer anymore. And I just threw away a whole bunch of CDs that I had in my cupboard the other day because I'm like, I can't even read these anymore. I still remember when I was an undergraduate in college and I got my first zip drive. And I was like, this zip disk can hold 100 megabytes. My life is good. I'm never going to need anything more. And then they came out with the 250 megabyte zip disk. And I was like, wow, this is amazing, right? So things change pretty rapidly. 1995, DVDs. And now most people, you're using thumb drives, you're using external hard drives. This statement from the Borer paper is kind of funny. As hard as it is to believe today, we can foresee the day when CD-ROMs might be difficult to read. My computer cannot read a CD-ROM drive. Somewhere in my cabinet, deep down in a dark corner, is a USB CD drive that I could use if I really needed to. But the point here is, consider the way that you're actually storing the data. And this is, how are you storing the data in the field? How are you storing the data when you get it back from the field? How are you transporting it from one computer to another? You don't want to strand your data on one of these devices that then becomes obsolete. This is sort of a longer term consideration. I get emails from the USU IT network manager's email list every year saying, hey, does anybody have a 3½ inch floppy drive that's USB? Because such and such an investigator has data on a 3½ inch floppy disk that they really need to get off, but we can't find a computer that has a drive that will read it. So just think about that. Taking this a step further, so how are you backing up and preserving the data that you're collecting in the field? So here's an office that has a desk full of external drives. And is this really the best way to sort of be backing things up and organizing things? Some of the potential problems are, well, what if there's a fire in my building, which has actually happened at the Utah Water Research Laboratory? What if I drop one of those? What if it just all of a sudden one day totally barfs in my hand, which has also happened to me with an external drive? With external drives, my experience has been it's not a matter of if they're going to fail, it's a matter of when. And also, there are disasters that happen. So if your only copy of your data is sitting on your laptop computer or on an external drive in your office, that's probably not the best plan. So when you think about backups, number 1, have a plan. Number 2, stick to your plan. Number 3, test your plan. And I put this in red here because it's really preferable to test your backup plan under non-failure conditions. Like, I didn't just drop my computer in the parking lot of the water lab, and now I got to figure out whether my external drive backup is actually good. Test your plan and make sure that it actually works. And I've got Betty Rossum's 3-2-1 rule here. So Betty Rossum just retired. She was the data librarian at Utah State University. And she had this rule that said, you should have 3 copies. You should use at least 2 types of storage media. Probably one of those should be cloud and one of them can be your hard drive. And then make sure you've got at least 1 copy off-site such that if anything happens to the building that you're sitting in, you've got a copy somewhere else. This also extends to things like lab notebooks, research notes, field notes, right? There's a time when those are really quite vulnerable before they've been entered into a digital format, that if you were to lose those, you've lost a lot of work. And I'll also note here, don't trust or rely on hardware redundancy like a RAID array or something like that, because I've also been bitten by the fact that my RAID array failed, and now I've lost pretty much everything on those drives that I was sort of counting on. And sure, if one of your drives fails and you have the right kind of RAID array, you can plug a new drive in there and it rebuilds everything. But if 2 drives fail, you're pretty much host. So don't rely on hardware redundancy. Now, some considerations here just to think of in the back of your head. What do you need to be preserving? Where is it going to be preserved? What's my backup plan? Does anything need to be in version control? Think about source code that you might be writing, scripts that you're creating to analyze your data. Do you want to be using a system like GitHub to do version control? And then also, I think for those of you who are affiliated with CZNet, you should be having conversations with your local data managers and the investigators in your groups about what your obligations are for data sharing with all the things that you're doing as you're working, what sort of considerations there are for security and access control. Do you have sensitive data that have any sort of personally identifiable information or human subjects data that you need to worry about? Have you purchased any data that are subject to license agreements that you may need to consider? And then how long do you need to preserve things? Are there intellectual property issues, and who are the responsible parties? So many of these things should be spelled out in the data management plan for your cluster proposal, or if you're affiliated with another project that has a data management plan, have a look at the data management plan and make sure you understand what's actually in there. And if you don't understand it, we're happy to ask or answer any questions, and I'm sure your local investigators and data managers are also happy to answer any questions that you have. So to the cloud, right? None of us are really storing most of our stuff on physical media anymore. We're using the cloud because it's convenient, it's accessible anywhere, it's cross-platform, got good data sharing, it's low cost. But have you ever read the privacy agreement associated with Google Drive or Box or Dropbox? You might be surprised about what's in there. You're limited if you don't have an internet connection. You've got storage and it's great. It's easy to move things around. It's easy to share things, but the file formats and semantics that I mentioned before still matter. So just keep those things in mind. There's better opportunities now for data sharing and preservation associated with actual data repositories. And these are data archives, repositories. You've got functionality for collaboration and archival preservation in a way that data sets can actually be cited. It's hard to cite something that's just in somebody's Google Drive somewhere. They're still very much discipline specific, and the impact of your data is going to be higher if you choose carefully. We're going to recommend some specific repositories for the CZNet project, and we've got some upcoming workshops talking about those specific repositories. But for others who may be working for other projects or on other work, things to think about are like, does your research sponsor require that you put your data in a specific repository? That does happen sometimes. Does your specific scientific discipline have a repository? So like if you're working in hydrology, a lot of people are using HydroShare. It's discipline specific. Everybody knows that it's a place that you can put your stuff. And it's usually better to have your data in a disciplinary specific repository because it's with other data where other people are likely to find it. And then of course, when it comes to code, a lot of people are using GitHub, and there are ways to actually make your code citable in the same way that you can make data citable. There's still some challenges with repositories, like how to best use a repository. This is unfamiliar to a lot of people. How to avoid data misinterpretation. So if I put my data in a repository, how do I know that there's information in there that's going to help people understand what they can and can't do with my data? Size limitations for individual users. Some repositories have quotas that you may have to work around. And then what's the level of required metadata of the repository? Most of them have required and optional metadata requirements, but where do you set the bar, and how much time do you want to actually spend describing your data with metadata? Some repositories actually have data set review and curation before things are made public. A good example of that is EarthCam. You submit something to EarthCam, it gets reviewed before it actually goes public. And so some repositories do have a process like that. All right, I'm going to round out my presentation today with a discussion about effective metadata. So let's go back to that statement about do not underestimate your ability to forget details about a study. And these are things like, well, when did that tree that was stuck in my stream cross section get removed? Or, all of those sorts of things that maybe a year down the road you might forget because you may not analyze your data until a year or two down the road. So metadata is a love note to the future. I saw this in a presentation once and I stuck this in here. It's the who, what, when, where, why, and how about your data. And it describes the content, quality, condition, and other characteristics of your data. You need to think about the content and the formats. So what metadata are needed when we think about content? What are the details that make the data findable in whatever repository you're going to put it in? And then what are the details that make the data meaningful to somebody who might find that metadata, find your data, and then want to actually use it? And there's some considerations here, like if I'm writing my data in lab notebooks, how are the metadata actually going to be created? Am I going to transcribe my lab notebooks? Am I going to have help curating my data by a local data manager? And do I need to be communicating back and forth with that person about what the metadata are? Or are some or all of my metadata being generated by a sensor or an instrument? Some instruments output ancillary data files that are just metadata about the data file that got created. So what format to be used for metadata a lot of times is chosen by a specific community. Everybody's doing it the same way. It could be dictated by an agency if you're depositing data somewhere. Likely it's going to be dictated by a repository into which you deposit the data. And I want to just throw this in here because a lot of you are also dealing with sample data, and samples also have metadata associated with them. We're going to have an upcoming workshop that's going to talk specifically about samples, sample registration, sample metadata, and we've already talked about this before, but we'll do this in more detail. There are standards for metadata associated with standards with samples that help you document what the samples are, all of those sorts of things. And there's some best practices for sample and collection cataloging that we'll talk about a little later on. There is a golden rule associated with sharing data and metadata. When you provide data to someone else, what types of information do you know that they're going to need to understand the data? And then when you receive a data set, you want some information that's going to help you interpret that data. So that exchange of providing and receiving data should tell you something about how well you should be describing the data. Also, you have to decide how many emails do I want to answer and how many phone calls do I want to take to describe the data that I just put out there, because people want to reuse it and they got to know what they can do with it. So here's some questions and considerations that you might think of. Why were the data created? What limitations do they have? What do the data mean? How should the data be cited? Most repositories now have a specific section that says, here's how to cite these data. When you're receiving data, you probably want to know something about are there gaps in the data? What were the methods used? Are there any fees associated with the data? How can I actually use the data? Can I give the data to somebody else? Is this license that I'm downloading the data under restrictive? Those are all considerations. Now, I want to talk a little bit about planning here, because just like occasionally we run into issues when we're thinking about scientific papers where, we do some work and we talk about a lot of ideas with people, and then maybe a year down the road, we're getting well along with the research and we start thinking about submitting that paper, and then all of a sudden it becomes really muddled and unclear about who contributed to that paper along the way, and we don't know what the order of authorship should be, and we can get into some really sticky situations, and people can have feelings and professional reputations hurt if we don't address the questions related to timing, organization, and authorship up front. So I encourage you to have these conversations really early in the process about which products are going to be generated and shared. Are there any sensitivities around any of those products that you need to be thinking about? And by sensitivities, I mean not only like human subjects data and personally identifiable information, but also at what point are we going to be ready to put those data out there, given that somebody's writing a paper about those data and we want to make sure that we get our paper out there first, right? How are those data and files going to be organized? Who is responsible for the data and metadata creation and curation? Who are going to be the authors associated with those data when they go into a repository? All right, I'm going to leave you with the Stephen Hall story. So Stephen Hall was a postdoc researcher that worked with us on a large collaborative project across multiple universities. This is a couple years ago now. Stephen went out to the field, he collected his data, transformed it into a shareable format. He had a little bit of help, just like any of you who are collecting data. You've got a data manager, most likely working with your project, who can help you deposit your data set in an online repository like HydroShare. Stephen went to HydroShare, he made sure that his data were there, the files were good, his metadata was correct, but he wasn't ready to put the data out there yet. So he kept his data in HydroShare private. He went ahead and submitted his paper for publication, and he responded to the reviews on his paper. And one of the reviews that he got back was from the editor of the paper that said, "We're happy to publish your paper as soon as you have deposited your data in a reputable repository and it's publicly available." So Stephen pushed the button in HydroShare to publish the data. He got a digital object identifier and a citation, and he put that in his paper. And the one thing I wish Stephen would have done that he didn't do, he put the reference to the data set in the acknowledgements section of his paper. I wish he would have just cited this directly in the references of his paper, just like he's citing anything else, so that somebody could go to the references, click on the link, and go directly to his paper. But the link to his data set in HydroShare is right there in the acknowledgements, and somebody wants it, they can access it. And now his paper's available, it cites the data's available, he's got a linkage back to the paper. And so Stephen's got this nice two-way linkage between the data and the paper. Okay, quick summary, and then we'll open it up for questions with the last few minutes we've got here. So number one, don't mess with the raw data, use descriptive file names and headers, archive your data in non-proprietary data formats, consider the data entry, automate the analyses any way you can with scripts to make sure that it's reproducible. Think about how you're storing the data in the field, in your office, online, for archival in a repository, and then make sure that you're considering effective metadata. And if you're following these steps and some of these ideas that we've talked about here today, it's going to help prepare your data sets for deposit. It's going to improve the quality of the data sets that you deposit. And it's going to improve the likelihood that somebody else is going to, number one, be able to reproduce the work that you're describing, the papers that you're writing, but it may also increase the likelihood that somebody's going to reuse the data for something else and build on the results that you've created. So with that, I will open it up for any questions. And I'm going to stop sharing. I don't know if there's anything that got posted to the chat or if
Nothing
anybody
in the chat
would like
so
to.
far.
Okay, great. Are there any questions from anybody? All right. Well, not hearing any then, we will wrap up this recording. This will get posted to the CZNet website. And next week, we're going to have another one of our data help sessions. So we'll be online again for any questions that you may have on a one-on-one basis. Bring your data sets, bring your questions. And then we'll continue with our next topic in 2 weeks, which I believe is related to sharing data sets in HydroShare. So thanks everybody for coming, and we will see you again next week.